this video I am going to talk about this robot. You might have seen it before in my last vlog, or even before that in the 3D program. But here's the real version with some good lighting on it. And what I'm going to talk about is basically how it works. But you should actually know how it works, because I have explained it in a previous video in more detail, but I'm going to show the practical example. So as you can see, from first thing is that it's a very basic body. It's just two sheet metals bent in to form some sort of eye shape, and this is basically the flange over here, and these are the mounts that connect the motor and the gearbox, so it kind of clamps it down. It dampens the vibration and such, but if you switch it around you can see it better. These are the motor connectors, and here you see two electromotors, one here and one over here. It's clamped down with these mounts, and it connects directly into the gearbox. As you can see over here, this is still the motor, and this is directly on the gearbox. This is to convert the power into torque, well, the rotation into torque, because you don't need much rotation on this part, or at least it doesn't have to be very fast. Then there is a drive shaft in here. You can't see it, but there is another piece. I'm not sure. It's a round piece. This piece that goes all the way through here, and you can see it move, kind of. You see it move, and this is independent from the drive shaft, because as you can see I can move this, but because there's tension in the spring, this moves as well a little bit, but actually it's independent. I'm not sure if I can show it, maybe better on the other side. As you can see, it's independent and still rotates. And basically what's the magic in here is that the drive shaft goes through this piece, through here, and it connects to here with a single bolt. And what that basically is, this piece over here, is that it's the flange for support, it's the drive shaft, and it's the steering shaft for the legs itself. So it's basically 3-in-1. It was a pretty complicated piece, this whole area, and that's basically the working function. And as the motors turn on the side, as the motors turn, this turns, and then this turns, and if that turns, if this turns, then you can see a rotation into linear transformation, and then basically this gets put on tension, and when that's on tension, the whole robot becomes smaller, and it has a lot of stored energy in its legs. Therefore it can make a jump move But as you can see also, we are missing this piece. I don't know if we lost it or something, but it's basically one of the reasons why it doesn't work right now. Another reason is actually software related, because as you can see there's a big board in here and it does all the driving of the motors. I'll take it out in a second so we can look at it a little bit closer. And what happens on this board is there is the motors. The motors connect into here. The battery connects in the back, right here. And there is stabilization. Here's the accelerometer that it senses the tilt and all the other angles and the acceleration, of course. And there's also a servo drive in here. As you can see, this cable that connects here. Here the cables connect that drive these servos. There's an internal buck converter that supplies power to the servos. And there's a lot of other stuff in there. One of which is an inverter IC. It inverts the Schmidt signal from these photo interrupters. And what they do is, as this turns, it counts the amount of holes it skips. And there are 50 holes in here. 25 is therefore half a rotation, and half a rotation is maximum tension on the spring. Another important reason for the encoders is that maybe the gearboxes and motors are supposed to be the same, but in reality nothing is exactly the same. Therefore one side could be faster than the other and you would get imbalance, and that can be seen with the sensors and with the tilt sensor. Therefore you can do vectoring on both motors because they're independently driven, and so you can make sure that it doesn't tilt over or it jumps sideways, maybe just a little bit, a couple degrees. But now with active feedback, with the encoders, the sensor inside, you can basically know whenever something is going wrong. And it is all stabilized via microcontroller. Therefore the calculation can be very fast. Also on the bottom we have a distance sensor. Therefore it can monitor the distance between ground and the robot itself. So that's pretty self-explanatory and simple. But we haven't actually included it in the programming just yet because we don't really need it. So basically we have a lot of sensors in here, more than any of the other teams did. They didn't have any sensors probably. We have these servos which have their own feedback, their potentiometer feedback. We have the encoders, we have the tilt sensor, distance sensor, and And that's about it. There's also a lot more going on in the software than just these sensors. Alright, so here we have the board taken out of the robot itself. And as you can see, first thing, we have two 1000 microfarad bulk capacitors for the huge ripple created by the motors. It's about 80 amps, because as you can see we have 8 MOSFETs here. There are 2 full bridges. This is a single full bridge and this is the other full bridge. Here we have the buck and power supply section. Here we have 2 inverter ICs. Here we have the sensor itself, and of course a separate microcontroller module. So we can try turning it on. So here we have the almost 12 volt supply, and let's try. It might spark, or the power supply might go in overcurrent, because the supplied voltage is coming from a very weak power source. So let's try it. As you can see, it just goes into a short circuit protection, and there it goes, because basically it is a short circuit if the capacitors aren't charged. And as you can see, the module is fully turned on. Alright, so I've plugged in the microcontroller to the computer, and let's take a look. So as you can see, there's a lot of sub-programs in one single program. For example, this is the sensor part only. Then we have a separate servo part, a separate PID controller part, empty motor controller part, and the main part. So what if we take a look at the serial monitor, and we engage the serial monitor, and you can see sometimes it fails, but we can try to fix that. I'm not sure what this is that it failed, because it failed in the past as well. Maybe it's just re-uploading. Maybe we need to reset. Take it out and put it back in. Maybe now it works. Yeah, you see, now it works. As you can see, if I turn off auto scroll and go all the way up, this isn't calibrated for the desk I'm sitting on, therefore the values will be off, because it's calibrated for the robot. And basically what this is acceleration. The first 3 are acceleration, and this one, the last 3 are the gyro, the angles. So here we can see the tilt angles and the acceleration. This is gravity. It's working the x-axis because it's tilted this way. Usually it's calibrated for a flat surface, but now it's set up straight, so we had to change this in the calibration. But let's put the outer scroll back on and let's see what happens if we tilt. Or first I can open the plotter. It's more visible this way. Right, so let me tilt it. And as you can see, it stopped working there. Let me try that again, maybe. I think there's a mechanical problem with the connection. So here it is with a higher voltage motor. So this is not the low impedance drill motor, this is just a high resistance motor, therefore it doesn't do much. But as you can see, it's doing pretty well so far at 12 volts, even though this can handle up to 50 volts or something. I can barely stop it even with my finger, and it's only at less than 50% duty cycle, I think, at 1 kilohertz. So I'm going to try different frequencies. So as you can see, here we have a very simple program. 1 kilohertz, 150. Let's change that to 5. And then we can also see the influence of resonance frequencies and time constants. So let's see how the motor behaves at 5. So there's obviously a different sound, but I can easily stop it with my finger. And this is still at 150 for the duty cycle. So that's not, I can easily stop this. The MOSFET's not even warm, even though this is not good for the MOSFET. If you stop it, it's very bad, because now it doesn't take any voltage, but still takes current. Current is going through the MOSFETs, and the voltage is also across the MOSFETs. But luckily, and also if you do this, the current increases. I can show you that. It doesn't change very much right now because there's not enough power. I'll change the duty cycle. Let's change the 150 to 100. Okay, can still probably stop it with my barely again. It's much harder to do now. But now we can see the current more clear. Can see 131. Almost half an amp. It's going into current control mode. I had to autofocus that. MOSFET's also not warm, so that's fine. This was able to do 80 amps. The whole double full bridge is therefore 40 amps per bridge. But yeah, now it's much more difficult, and you're probably thinking, what would it do then at 1 kilohertz? So let's change that back to 1 kilohertz. It's still at 1 kilohertz. And it goes into current control mode much faster as well. But same thing. There is an ideal frequency for every motor, and you need an inductance meter for that, and I didn't have one, so I didn't know the inductance of the other motors for the big motors, so that was kind of a problem. And what happened was I just set a random frequency to see if it started moving, and it didn't. It just went whining like this. And as you can see, the current just ramps up. Now imagine if that was 40 volts or 40 amps, 12 volts. That's a lot of stress on the MOSFETs. And what the MOSFETs did was they literally exploded. And that was one of the reasons why the robot didn't work, because we had a lot of setbacks with that. MOSFETs exploding and just not working. So any type of transient filtering on the MOSFET gates is very good. Let that be a lesson that you must also keep in mind, that the transients can be extremely dangerous to MOSFETs, because they will stop working. And that was basically it for now, I think. I'm not sure if you want to see some waveforms. I can show the waveform on the scope right here. So let's put it on ground. So let's see. So it's now just on the positive of the motor. It's at a very high duty cycle, so you can expect almost, as you can see. This part is not very good, it's resonating. We can see what happens if we change the frequency back to 5. This lamp. As you can see, it's much better. This is what you want more, because what we had then it was not good at all. Let's try something else. So this is 7. As you can see, a little bit better. Maybe 9. It's still the same about. So let's try something insane like 20 kilohertz. This is the tiny bit of inductance it has. the drop. But as you can see, it's going perfectly to 0. There's no inductive spiking, maybe just a tiny bit over here. And what happens if we apply a load? The waveform actually stabilizes. So this is a pretty good waveform, I would say. So yeah, with motors it's very important that you know what frequency, what switching frequency you must have, and what your motor can handle. Let's see, if you go to 1 again. There it is again. We single that. As you see, very bad voltage ripple. But what happens if we put a load on it? Wait, need to start it now. As you can see, the transient removes. So with load is not very, it's not a big deal, but you must keep in mind of the resonant frequency. It's basically with everything, every inductive load is an inductive load. You must keep in mind with transformers, inductors, and basically everything. This is a special case of inductive load because it's a motor, of course. It's a mechanical piece. And maybe what happens if we lower the frequency even more? So this is going to 500 Hertz. As you can see, this is even worse. But what happens if we put a load on it? It does fine, almost, but this is not very good. Actually terrible. It is collapsing. But if you put a load on it, it's doing good. Basically, it's working, but it's going into current control mode and not doing anything. So let's just remove that. So that's also a little lesson on motors. Maybe we can take a second motor and see what happens with that. Okay, so I've taken a smaller motor, and this one is obviously a little bit stronger than the last one, probably because it's smaller and the windings have less resistance. But as you can see, this is at 5 kilohertz. And maybe you can hear it or not, but the whine is pretty bad. Now change to 9 kilohertz. It's a lot better actually. At 9 kilohertz. As you can see, it's also 9.00. Previously it was at 5.4, therefore there was this fall time or rise time of the motor itself was being counted in as something, as I don't know. Let's try 1000. And there it is again. And you can't stop that with hand. It's going pretty hard, but as you can see, there's also a correlation. Let me stop this. There's a correlation, as you maybe see, between the switching frequency and the power of the torque of the motor itself. Basically, I think it's because of the switching time. There's a longer period of DC on time. Therefore, the motor is getting more 100% duty cycle DC per second instead of the chopped up pulsed DC. I think that's one of the reasons, and that goes hand in hand with the LR timing of the windings, because they have a resistance and an inductance, and that's the reason why you need to know the inductance of the windings itself. But 1 kilohertz, you saw the ugly transients, but the motor was pretty powerful. If I couldn't stop it. Yeah, I can't stop it. But if we try a different frequency, so this is 10 kilohertz. And I still can't stop it, but it's going easier. Also the current consumption now. Let me put it out of focus again. As you see, I try to stop it with the hand, and the current is basically just going up by very little. And if you try a different frequency, let's try the 1 kilohertz again. As you saw there, power supply going into current control mode. So maybe I'll do a more educational video on motors, but for now I think this is pretty good knowledge so far to address that motors aren't as simple as they look, because I first underestimated motors a lot actually. I thought you could just take a square wave, put it in a motor and it works, but it's more difficult than that actually. And perhaps in the future I'm going to make my own brushless motor, just using steel lamination plates and then laser cutting them to make a stator, or perhaps the rotor. No, I think it's the stator, and just using copper to wind it all around, and maybe even make a electromotor that's capable of tens of kilowatts, and that's definitely I'm going to try someday. There's going to be a lot of control and power switching, so it has to be fun. But that's basically what I want to say. I hope you learned something, and I hope you enjoyed it, more importantly. If you have any questions about motors or robots or control system switching, power switching, just leave them in the comments. And I also have a Discord channel where I randomly, or well, I'm basically there everywhere, every time, and we basically discuss projects and other things such as future projects, railgun stuff, coil gun stuff, that kind of stuff. It's a lot of fun, and you should join if you want to. But yeah, that was basically it. If you want to know more about this, maybe you can also leave them in the comments. If you want to know anything at all, leave it in the comments. And thanks for watching. I'll see you next time.